here, Shui from Red Hat virtualization team, and today I'm going to, nice. So today I'm going to talk about device assignment. Twice. Making some sound. Okay, so basically it's about nested device assignment. For example, when you want to assign a device for more than once, especially, for example, to a nested guest, possibly you can consider something like this. So I'll give a very quick background information. So what is this talk about? Is about device assignment, of course, but only on the DMA part of it, because we know that device assignment can contain many things like interrupt, MMIO configuration spaces. And in this talk, I'm going to only cover about the DMA part of it, because we are only talking about really stuffs with IOMMU inside. And the second thing I'd like to talk about is the IOMMU itself. So basically, this can be seen as a slightly enhancement to the existing device assignment, but it would allow us to assign the device for more than once. And basically, the thing that we have done are only in the IOMMU implementation, but not the device assignment, but is supporting the device assignment. So as we know, maybe most of us, that these two features are actually there for a long time, but they're not really working well together. If you try to boot something with two features enabled, you will get some, you can't really boot into BIOS, I think. So the problem is that device, after we have IOMMU in the guest, we need per device page table for that. And for an assigned device, it will do DMAs directly on the hardware. Basically, it means that it cannot see the guest page table, and we don't have a good way to notify between these stuff. So basically, we need to connect these two components. One is the guest page table for the device. The other one is the real hardware, and there is actually a real IOMMU in the host. We need to connect these two stuff and make sure that page tables can be somehow related. And this seems to be a bit complicated at first glance, but should we need it, or say whether we should bother with it? So these are some of the issues that we have encountered that might use this feature. For example, the Userspace drivers. We know that there are quite a lot of Userspace drivers that are driving all kinds of devices, no matter block or network or even something else. And these drivers are just normal processes. So it can be harmful, or say there can be bugs inside. We cannot crash the system only if the process is broken. And basically, we know we have IOMMU to protect it from the processor's point of view, because we have instruction protections like that. We can have something like segmentation faults. We were assuming it's safe because we have Spectra and Meltdown, but basically I will just ignore them in this talk, so it's safe. But from the device point of view, this is not really true, because if without an IOMMU in the guest, and if you are running a DPDK application in the guest as well, then you are possibly either using UIO or VFIO no IOMMU mode. And both of these modes are unsafe, which means that a bug in the process can crash the kernel in the guest. That is not good. So basically, when we do that, the guest kernel is tainted, and no one will maintain it. We'll be able to maintain it because anywhere can go wrong. So basically, this is a security issue that we need to solve if we really want to maintain the guest kernel and to be able to do something with that in production environment. And the second one is about the device assignment for nested guests. So if we want to assign a device to the first level guest and even to the second level guest, if we think about it, we'll see that it's not possible to do that on the second level, because we know that a VFIO PCI device will require IOMMU in the host to do device assignment. So the same thing happens to the L1 guest. If we don't have IOMMU in the guest, we can't do the device assignment. So it's not really, for this one, it's not really a security problem, but really a functional issue. that we can't do that because we need a static mapping like R2GPA to HPA for the second level so that the host can know how to do DMA. So basically, if we do a device assignment for nested, we can't without these two features working together. So I'm getting a bit faster because of the timing, so maybe I'll just skip some of the things. But basically, I'm talking about this. So this is a picture. It shows how the IOMMU in the L1 guest plays a role there. It provides L2 GPA to L1 GPA mapping, and the real one is providing L1 GPA to HPA. Basically, we need to do something else, actually, but we'll talk about it later. So what if we want to do this? How? We can have a look at what we have already. So this is the DMA framework. It's very simple, actually, not really a framework. When the emulated devices do DMAs. So it's quite simple, basically 2 steps. The first one is the located DMA buffer. It means in the guest side, of course, we locate a buffer in the guest, and we trigger the DMA, and the DMA will be carried out by the QEMU memory core API. So it knows how to translate this GPA to HPA or HVA, whatever. Then we can do the DMA as usual. That is a really simple scenario, but I'm trying to get it a bit more complex. The second one is about still emulated devices, but what if we are with the vIOMMU inside? So we can see that there are more steps. Firstly, we need to allocate the buffer as well. But at the same time, we'll need to allocate the page table for the device. I mean, just to set up the pages that we'll need for the DMA buffer. That's still also done in the guest, and that page table is, as I mentioned, in the guest memory. So it's not seen by the host, but there is no problem because we're using emulated devices. And later on, we do the DMA. And this time, memory core API will not understand what's that address because it's called an IOVA address. I think I skipped some of the terms of IOMMU, assuming that you know IOVA, which is the IO virtual address for the IOMMU for the devices. So the QEMU memory core API knows, doesn't know IOVA, but it can ask the vIOMMU to do the translation to translate that address, IOVA address into GPA, and after that it knows. And that translation is actually by querying the guest page table. So that is mostly how the emulated devices are done with DMAs. So the third scenario we can have a look about is the signed devices. So this is when we are not with an IOMMU in the guest. So this is the general scenario of device assignment when DMA happens. Signed devices are a bit special in that we have to set up the GPA to HPA mapping beforehand, even before start QEMU. We need to set up this in the host IOMMU. So there will be a static device page table there per device. And when we do DMA, basically you are doing the same thing like emulate devices. So we first allocate the DMA buffer in the guest as well. And no need to set up page tables because there is no IOMMU inside. And when we do DMA, we don't really do it by QEMU, inside QEMU. It will trigger a real DMA in the device to do that DMA on the real hardware to the RAM, to the host RAM. And that can be carried out only if we have already set up the static page mappings beforehand. I mean, this is mapping the whole GPA range to the HPA range. So no matter where you DMA to, or read or write, you can have the correct translations on the host. And I still kept the memory core API, but you can see that it's just it's not used at all because it's not aware of that at all. So what we need is to have the device assignment alongside with IOMMU in the guest, which looks like this. So this is a bit complicated, but not really. So we see that in step 2, it's similar to emulate device as well. Firstly, we allocate the buffer and we'll set up the page tables. And before we do the DMA, right now we need something like a PV interface right now, but it can be something different. For example, page protection. So it can be no PV device, no PV message at all. For now, we can assume there is a message, which is step 3. That is the special part. So we notify the vIOMMU about this mapping. That is very important step to allow these two IOMMUs to talk. So every time there is a page mapped for the device, we can know that, and we can do the synchronization or whatever we want inside the host. Basically, that's what we do now. We receive this map message at step 3, and we synchronize, we call it the shadow page table for the device in the real host IOMMU, and we return. This should be a synchronized operation because we should have everything set up before the DMA happens. And after that, we trigger the DMA as usual. And this time, the DMA will be with IOVA as the address. And this time, it will be translated as IOVA to HPA on the host directly. So that will be done. So this is something that is in the host IOMMU page table. The first one is is when we are not with the IOMMU in the guest. And the second one is when we are with it. Basically, it's the so-called shadow page table. If we actually it's the same one as the one in the KVM, but just not really the same, exactly the same, but the similar thing with what we do with soft MMU in KVM when we are not with EPT, but that's basically how it looks like. So as we have already mentioned, if you still remember in the last graph, there is step 3 that we notify. When we set up a page for the DMA buffer, we will notify the host, actually the hypervisor, to know this new mapping. And this is the trigger point to synchronize the shadow page table for the devices. So this part is very important for us. So the first solution, as I mentioned, we don't really need a real PV interface there. We can actually trap, as far as I know, we can do that to trap a page. But we need some better interface, or that's complicated work. For example, if we are using KVM, maybe we need some new octals to support this. I'm not sure. And of course, we can have something like Userspace, but it's still, Andrea had some work on Userspace to allow the write protection. Maybe that can be something in the future. I'm not sure. Basically, as long as we can trap the page faults, the write to the pages, we can know the page table changes, so we can synchronize the page tables. But now we are using a far simpler way, which is called caching mode on the Intel platform. So basically, this work will only work for Intel because of this, because we are using a specific mode defined in the VTD spec to do this emulation. And that is helps us a lot because, for example, it's very simple. We don't need to change KVM or any other. We don't need new weapons to do that. And there is already existing guest drivers to support this caching mode, though with bugs. But basically, it works. So the only thing is that it only works for Intel. So when we have, for example, ARCOG is working on the SMMU side of the nest of this similar stuff. Basically, a shadow page table will require something else. So they are people are doing nested directly. So as we have already mentioned about shadow page tables, what I was curious about is how is this different comparing to the KVM MMU shadow page table? So I did a very quick comparison. And so maybe the target is different, of course, and we don't allow page faults for IOMMU yet. But I think PR is a page request interface, something like that is in progress. So maybe in the future, hardware will allow to do page fault even from the device side. And how do we do because there are shadow page tables, we need to trigger the synchronization. And how do we do that? For IOMMU, we have page faults because that's naturally supported. And for IOMMU, we don't have that. And we have that so-called caching mode and or any other explicit message that we can have, for example, write protection. So the page table formats can be very complicated for IOMMU, at least for x86. So basically, I'm only talking about Intel. And for IOMMU, it's simple. We only have one. But we don't have that problem on complexity of squashing page tables into one because we are, after all, using something like VFIO, octals. So we don't need to care about that, actually. For the cost, IOMMU shadow page synchronization is relatively small, but although it's complicated, but it can be small because everything happens in KVM, and basically we do everything and return to the guest mode. For the IOMMU is really a long code path, so basically the codes can be simple, but the code path can be super long. We can have a look later. And do we need the previous state? That seems a bit a strange question here. So why a shadow page table needs a previous state? I'll try to explain later. So we need a previous state here, but for IOMMU, we don't need it because I'll explain. So this is how the code path is when we are doing shadow page synchronizations for devices. We can see that this is an example of when we map a single page in the L2 guest and how this synchronization event is delivered. If we see it a bit into details, we will see it very similar like all the I/O paths, no matter network or block I/O paths when we are not with vhosts, not to care about vhost X or vhost Y. Basically, that's the thing we have for I/O path. And when we have vhost, like a vhost NAT, we just connect these two kernel components together, and that will be faster. We can reduce lots of context switches, but for now it's super slow. I'll show some numbers later on how it can be slow and how it can work in some cases, I mean on the performance side. Okay. So about state cache. So as I mentioned, IOMMU shadow page tables are a bit, it's a bit different that we need a state cache because we cannot really operate on the page tables really. We can only add a page or remove a page. So if we think about it, we can't really do anything like change a page table. So we need to keep a previous state of the page tables. I think time is getting close, but I don't see it. Yeah. Okay, I'll just go quickly. Quick status updates, some facts. So we can do a quick comparison between emulate devices and design devices from the IOMMU perspective. So when there is an IOMMU in the guest, the performance can be very interesting and different for these two kinds of devices. For emulated, when we are mapping, we are so fast because we don't need interceptions from the hypervisor's point of view. Basically, we set up some PTEs and we just do the DMA. However, it will be slow when we do the DMA because we need to translate on the fly. So the setup is fast and the I/O is slow. And for sign devices, it's interesting in that when we map the page, it will be super slow, as we already mentioned the long code path. However, after it's set up, the DMA can be extremely fast because, everything is already set up. So the I/O will be merely the same as when we are doing things like on the hardware. No matter how many guests we nest. For example, we nest 100 guests, and we assigned 100 times. As long as it can set up it correctly, maybe after 20 years, but the I/O will be super fast as well, just like on the hardware. So that's the interesting part. Basically, that's how shadow page works for IOMMU as well. And some performance. I'm taking XGB as an example. The kernel driver can be super slow, like only 20% of the performance. but we are doing this for user space DPDK mostly. So these kind of user space drivers are not affected because of the thing I have already mentioned, because the setup of the mappings are beforehand. So we don't do mapping changes during DPDK applications running. Future works, maybe we can have something like vhost IOMMU, for example, to connect. Okay. Is it time?
Can I have a question?
Yeah.
The 18% degradation is just passed through on the level 1 guest, right?
One, sorry?
The degradation
Yeah.
in level 1 is just as the pass-through with the NIC, regular pass-through to the guest, right?
With IOMMU inside and with it enabled. So normally device assignment performs super fast. I need to explain this well, because Alex's work is perfect, on the device assignment part, of course. And my work is dragging this down in some scenarios, but basically, sometimes maybe we need it for nested, especially on researchers. We don't need performance or whatever, DPDK. Yeah. Okay. So basically, this is a command line that you can try, and some versions that I would suggest, because there are some bug fixes. Otherwise, you will encounter problems. And for more information, please refer to this link. I think, is there a card or something? I didn't see that. It's 20 minutes, right? Questions? Yeah, question, please. Yeah.
The command line you told is this when the command line is the first level guest, right? In the guest you use regular QEMU, right?
Yes. In the guest, you can either use IOMMU or not. You can run the guest without R2 guest.
The second level guest, because
this
is a command line you need to run on bare metal,
yeah.
right?
Right.
And I have another question. Why are you using a split RQ chip? Is it necessary?
Yeah, let me think. Is it? I think it is for interrupt mapping, but I'm not sure. I think it can work without it if you are turning the interrupt mapping off. So basically, that's a dependency of that. Yeah.
Okay, so thank you very much. It's time for break.
Thank you.